Hi everyone, welcome to a presentation on Harvest Print, a technique that enables fingerprinting of battery-free backscatter tags. Let's start with the presentation. Current world is seeing an exponential boom in the number of connected devices. A majority of them relies on batteries for their operation, estimating global battery for IoT market to touch around 15.9 billion USD by the end of 2025. Most battery-based IoT devices consume tens of milliwatts. This means over time, their batteries need to be replaced, causing not just additional expenditure, but a negative impact on our environment. A key question here is, what causes so much energy expenditure for these devices? Interestingly enough, devices spend more of their energy on transmission. Hence, reducing the energy expenditure during transmission might be the right way forward. Backscatter is a technique that separates carrier generation from the tag and allocates this to an externally allocated infrastructure, thereby massively reducing the transmission energy expenditure. Some of these tags can have an inbuilt oscillator generating its own signal, which is then superimposed on an externally generated carrier signal. The backscattered signal is finally captured by a receiver and processed. Some recent backscatter designs allow operation at powers as low as 70 microwards by further minimizing the computational elements within the tag. This means that tags can now operate using small amounts of energy harvested from the environment. This also means that backscatter tags can be made even batteryless. However, as we stress, limitation in hardware and reduction in complex computations are very important for the tags to operate batteryless. In effect, we are compromising on the device's ability to implement complex protocols, and this includes well-refined cryptographic security protocols. This means even a simple two-way authentication to verify legitimate tag transmissions become extremely challenging. Instead, we need techniques that can preferably provide some degree of authentication without adding to the energy, hardware, or software cost. A simple solution here would be to make use of hardware offsets from tag oscillators, as has been done by multiple previous works. So let's see what hardware imperfections are. Consider transmission from two tags. Tag 1 with oscillator 1 transmitting a signal with a particular carrier frequency and a rogue tag transmitting another signal simultaneously upon being tuned to the same carrier frequency. The receiver, upon receiving the two signals, can observe minor shifts in the two transmissions. These shifts are due to small imperfections during the manufacturing of low-power oscillators. The oscillators, instead of transmitting in the frequency f to which it is tuned to, will be transmitting with an additional delta f that is contributed by its imperfections. By pre-configuring the imperfections in the transmissions from a tag, a receiver can identify which tag transmitted what. However, there is a catch here. The frequency at which the oscillator transmits is extremely sensitive to the voltage that is input to the oscillator. What does this mean? Minor variations in the input voltage supplied to the tag result in frequency variation in the tag oscillator output. To verify this, we took an oscillator and started adjusting its input voltage by fixed discrete values. As can be seen, the oscillator undergoes continuous shift with supply voltage changes. The shift in the offset can be either in the increasing direction or in the decreasing direction, which means that this is quite random for different oscillators. Hence, oscillators tend to show slightly erratic behavior for even minor changes in the supply voltage. So let's see why this is a huge issue for battery-free tags. Let me explain this using a simple illustration. Assume a tag being powered by an energy harvester harvesting solar energy. The harvested solar energy is actually stored by charging a storage capacitor within the harvester. A battery-free tag powered by the harvester actually gets its supply voltage from the storage capacitor. Draining the storage energy from the storage capacitor results in discharge. This means that the voltage that is actually input to the tag undergoes continuous variation with the storage capacitor charge and discharge cycle. So Harvest Print is a technique that monitors the oscillator discharge pattern. Let me be more clear. Let us consider a low power oscillator powered using a harvester harvesting ambient light and storing this energy in a storage capacitor. The storage capacitor supplies voltage to a low power tag oscillator. As can be seen, a capacitor discharge produces a frequency variation within the oscillator. This basically is the effect that the hardware offset produces with respect to the supply voltage variation. Our tests show that such patterns can be observed across tag oscillator configurations as well, thereby providing a potential for being generalizable. However, the more crucial question here is, can this oscillator pattern be used as a fingerprint? For this, the first check is, of course, the repeatability of the pattern. This means that a tag oscillator should consistently produce the same pattern across testing conditions. The tag should reproduce the exact same pattern across multiple trials with changing capacitance and across changing harvesting conditions. This is because no matter what the external conditions are, the tag finally ends up draining a consistent amount of energy from the storage capacitor. There can be, of course, changes in the number of samples within a pattern. For instance, a larger capacitor drains the energy more slowly compared to a smaller capacitor. Hence, the voltage drops are slower, taking a longer time to reach the lower input voltage, which means that the pattern can get stretched or shortened. However, they all seem to be reliable. Such a reliability proves that the pattern is exclusively a property of the tag oscillator hardware and can indeed be pre-configured at the receiver as a tag fingerprint across experiments. This shows what all the received samples are evaluated for to understand what is a pattern. The next test that we use is the uniqueness of the pattern. This is in line with the previous studies that use fixed hardware offsets for identifying transmission uniqueness. Since the patterns are a manifestation of offset variation with respect to supply voltage changes, this should definitely be unique for an oscillator. And this remains so even when two oscillators are powered using the same harvester parallelly, undergoing the same exact input voltage variations. Finally, we perform a proof of concept implementation of Harvest Print. The tag schematic includes an MSP430 microcontroller unit equipped with two LTC6906 oscillators. The oscillators are tuned to 101 kHz and 111 kHz. And having these two oscillators enable the tag to transmit in modulation schemes like FSK. The tag circuitry, including the oscillators, are powered using BQ25570 energy harvester equipped with a solar cell and a 1 megafarad storage capacitor. The test bed consists of CC1310 as the carrier generator, which generates a frequency at 868 megahertz. The carrier wave is actually reflected by our tag over here. And this is finally captured by a line SDR, which samples at a rate of 2 mega samples per second. We also parallelly monitor the pattern that is produced by the oscillator to see if the pattern that is actually reflected and the pattern that is produced by the oscillator are in par with each other. And this is the result for that. The matching patterns at the oscillator and the backscatter reflection actually proves that the tag oscillator patterns can indeed be used as a fingerprint. To complete the loop, we need to show how Harvest Print can identify the imposter transmissions from the legitimate transmission. As we have already said, the aim of Harvest Print is to provide a basic authentication to the legitimate transmissions, even in the presence of an imposter. To test this, we consider an imposter tag transmitting parallelly with an authentic tag. The oscillators within the imposter tags are configured a priori to match the frequency of the legitimate tag transmission. This is the result. Prior adjustment in the oscillator frequency ensure that receptions from both transmissions start at the exact same point over here. But later on, both of them undergoes discharge, which means that the patterns produced by the legitimate and the imposter tags become quite different after a point. However, this might need further improvements if more sophisticated adversaries are considered, which will leave as future work. To conclude, Harvest Print devised a technique to fingerprint battery-free backscatter transmissions without adding any additional complexity to the tag. For this, Harvest Print utilizes the patterns that the tag oscillators produce during the harvester's storage capacitor discharge. We can definitely consider integration of Harvest Print with more sophisticated security protocols to improve its performance further, making the tag immune to more powerful adversarial attacks. Thank you.